All right, so we move into chapter 8. Chapter 7 was, I can't remember, what was 7 all about? Something external flow. Now we move into chapter 8, internal flow, inside of pipes essentially, and maybe inside of ducts as well, but internal flow. Let's take a look at what do we have to cover. Well, we have section 8.1, hydrodynamic considerations. That is review. Flow conditions, mean velocity, profile, velocity profiles, pressure gradients, friction factors, fully developed, developing. That's all review of fluid mechanics. Again, I'll repeat, this class is not hard. It was the prerequisite class to this class that a lot of people stumble on because they finally go, oh no, not only do I have to learn the heat transfer when I have convection heat transfer, I have to relearn the fluid mechanics behind, or that's beneath, that's going on at the same time as the heat transfer with convection. So that's why this section's challenging, not because of the heat transfer. Then finally we'll get into thermal considerations, etc. What I found is this takes a lot of time. Today it's pretty much all review. So we have this big tank, and maybe there's an inlet region into a pipe. And the velocity profile in the beginning of the pipe is as sketched in blue right there. And it's pretty well uniform over the cross-sectional area of that pipe. And as we move further down the pipe, usually X is used to dictate where you're at in the length of the pipe, X equal to 0 all the way down. Well, let's just focus on the hydrodynamics. At a section down here, the viscous effects of the wall are propagating into the core region of the fluid. But at some point, when it's like at this distance, we'll call it X. So fully developed hydrodynamic. We're going to talk about that in a second on the next slide, but we review, there's a Reynolds number for flow inside of a pipe. Do you remember that? Rho VD divided by mu. But what is the V, the velocity for flow inside of a pipe? It's the mean velocity. So this U mean is this mean velocity. Well, what's that defined as? The mass flow rate divided by rho AC. All right, exactly what is AC? What's that C on the A for? Cross-sectional area. How big is the pipe of diameter D? What's the cross-sectional area? It's pi r squared or pi d squared divided by 4, isn't it? In terms of diameter or radius, that cross-sectional area. Good. So the mean velocity we're going to come back and revisit, but it's picked such that it's equal to the mass flow rate divided by rho AC. It's like, the way I like to describe it is, I like this simple way in order to calculate the mass flow rate. And in this equation, rho is easy, the cross-sectional area is easy, and this gives me the proper definition of the mean velocity. You come up here, that's what our mean velocity is. What's our length scale for the Reynolds number? It's decided, been decided. I'm glad it's like unanimous consent and everybody adopts. It's the diameter, the inner diameter inside the pipe. It's not like half of the world using radius and half of the world's using diameter and they're off by a factor of 2 from each other. No, I'm very happy to report simplicity here. It's just all diameter. So a lot of times you'll put a REL or an RED, some subscript on that Reynolds number to emphasize what's the length scale. Here it is, diameter. What is mu again? Viscosity, and rho is the density. Ooh, let's ask a clicker question. This is all review from memory. Maybe you don't have that good a memory, maybe you do. The critical Reynolds number for flow inside a pipe is either 2,300 or 500,000. This is pipe flow, people. Last chance for some to get correct. All right, there you go. I'm just going to shut it down and read it and weep. 23. Hey, how come they're picking 500,000? They're thinking about the previous chapter. What was the previous chapter? Flow over flat plate. The critical Reynolds number for flow over flat plate is 500,000. For internal flow inside a pipe, 2,300. All right. Another review question. Let's just throw it out there. Which of these are correct for the pipe flow? Is it A, B, C, or D? So is it rho use of MD over mu, or use of MD over nu, or 4 m dot over pi d mu, or all of them are correct? Either one. Let's go ahead and stop. Are we all correct? Well, what is this property nu? Is it equal to mu divided by rho? Yeah, that's all fluid mechanics. All right. Okay, so that looks like these two are good. I'm in a quandary. Is this one good or not? Okay, well, let's try this. Let's try rho u mean d divided by mu. If I multiply by m dot, I can divide by m dot. That won't change my answer. But m dot is rho u mean cross-sectional area of the pipe, is it not? All right. I multiply by cross-sectional area. I divide by cross-sectional area. That's pi d squared over 4. Did I do that right? So we get rid of the a sub c. We get rid of the um. We get rid of the rho. And we get rid of one of the d's. And we're left with 4 m dot divided by pi d mu. A lot of times you're given the mass flow rate, so it's a more convenient way to calculate the Reynolds number. So what's the best answer for all these? Congratulations, that's pretty high % correct. I'm glad. That was a tougher question. So how long is that fully developed, or the entrance length? How long is that entrance length before it's fully developed? Well, it depends if it's going to be fully developed laminar flow eventually or turbulent. It depends on the Reynolds number. So if the actual Reynolds number is less than the critical Reynolds number, you expect it to eventually be laminar flow. And a lot of work went into developing it, fully developed hydrodynamically. It's 1/20th diameter times that actual Reynolds number. That's the consensus. That's out of the fluid mechanics textbooks. How about if it's turbulent? Well, it's just 10 diameters. Very simple equation. In many, many applications, do you think more engineering applications are laminar flow in pipes or turbulent flow in pipes? Which one do you? Turbulent. It's turbulent. I mean, it's kind of like large pipes cost more money, so rush the flow through the smallest pipe you can afford in the sense of pressure. You have a higher pressure drop, etc. So a lot of applications are turbulent flow. Not all engineering applications, just the vast majority are. And it's a very simple formula to remember, 10 diameters. And a lot of times I've worked with different people, and they'll put a flow meter in, and they're very careful to put a flow meter such that you don't have some obstruction or some change in the piping system at least 10 diameters before you hit that flow meter. Because the flow meter, it counts on a certain profile, even if it's turbulent. It counts on it. And so, unfortunately, in some applications, they'll put in a flow meter 2 diameters after a bend. Bad news. Don't do it. Your flow meter won't have good readings. The accuracy of that flow meter, look at the paperwork that comes with it. It'll say, give me at least 10 diameters, straight run of the pipe before. And then usually there's also little criteria for straight run after the flow meter. Anyway, let's use these two equations. Somebody says, the Reynolds number is 200. How many diameters do I need to become fully developed? Well, you say, hey, that's laminar. I'll go use the first equation, and you find, oh, it's 10 diameters. Then somebody says, no, the Reynolds number is 2,000. It's just laminar. It's close to being turbulent. And I find out I need 100 diameters. Somebody else says, no, come in with 20,000. Well, you're already over the critical. So you're just back to 10 diameters. So it's not easy to say exactly what it is, but typically laminar flow in the high region of the laminar flow leads to long entrance regions hydrodynamically. Somewhere in the 2,000 range, you could have need a long distance for it to be fully developed. Let's press forward. Let's talk now about the mean velocity. How do I calculate it? Well, we said that the mass flow rate is equal to the sum of little mass flow rates over the cross section of my pipe. Well, I'll do little rings because the velocity I anticipate is a function of r only. So it's going to be a little ring for my area, and then I'll sum over all those rings from the inner core ring to the outer core ring. So that dm dot is rho u dA for that ring. And this is our favorite equation to replace for m dot. Basically, that gives me the criteria for what is the mean velocity. All right, we cancel the rows, and then we have the definition of u sub mean is 1 over a sub c times the integral of u dA. It's the area averaged velocity over the area of the pipe. That's what that is. And so somebody says, oh, I forgot, from calculus, what is dA? It's 2 pi r dr. Does that flow off your tongue pretty easily? You remember that? 2 pi r dr from calculus. And so you could put that in there. And then what is the area of a round pipe? 1 pi r squared. And there you go. So you would have to compute if you wanted to. Sometimes they'll have u mean is equal to 1 over cap r squared, the integral of u as a function of r, 2 r dr, from 0 to cap r. What's the difference between lowercase r and cap r? What's cap r? The outer actual radius of the pipe, yeah. Or I should say inner radius that the flow can go through, the fluid can go through. All right. Because a lot of times when you talk about pipe, you have an inner radius, then you have a wall thickness, and an outer radius. All right. Well, let's get that analytic solution for the velocity profile. How many people remember that it looks something like this? We're going to derive this equation, or there's the derivation to come up with that equation. How would you describe that equation? It's quadratic with respect to the radius. So if I go back and I say, here is my center line, and I'm going to measure r going out from 0 to cap r, the velocity profile is flat right there, and it goes to 0, no slip, and that's my velocity profile as a function of r, and it's quadratic in terms of r, isn't it? Sure, it's a quadratic profile. So how did you get that in fluid mechanics? What is the starting differential equation? What is that first equation? It's a differential equation. Where did it come from? It was in my fluids book, and because it was there, I trust it. No, where did it come from? What's a statement of? It's a statement of something. What's it a statement of? There's only a few differential equations in your fluids book. They're a statement of something. No, not viscous dissipation, but you're helping me. You're not taking the class, so you're exempt from answering. Sorry, Zach. It's going to be tough when we get to heat transfer. Come on now, who's not too shy? All right, I'll give you a hint. Either conservation of mass, something about linear momentum, or something about energy. One of the three. I think it's a mass equation. I think it's a momentum equation. I think it's an energy equation. One of the three.
I'll say momentum.
He's right. Yes. And it's either in the x direction or r direction. He's right. You're batting 1,000 in baseball parlance. This is great. All right, so this is our conservation, well, I shouldn't say conservation, it's our momentum, linear momentum balance equation. It's our F equal MA. So what's this? This is the F pushing it down the pipe. Is it accelerating when it's fully developed? No, it's just going on. So the linear momentum isn't increasing or decreasing. But what is this then? Well, that's resisting it. So you have competing pressure pushing it down, and you have the viscous effects holding it back. Well, this is a differential form. It's valid for any part of that fluid. You have two boundary conditions. Now you just love it. You can forget you're an engineer, pretend you're a mathematician, and separate, integrate, apply your boundary conditions. Away you go, and you get your analytic solution. That's it. It's math from there to there. Now, once you have it, you want to interrogate it. You think, well, where's the maximum velocity? Maximum velocity is at the wall or at the center line or somewhere in between. Center line. What is R at the center line? 0. Put R into that equation. You find this is the equation for the maximum velocity. Then I can make even simpler expression of the velocity profile. U max times 1 minus R over cap R squared. It's clearly a quadratic shape. Let's continue on. All right, from memory. For fully developed laminar flow in a pipe, the mean velocity, hey, we spent some time talking about that mean velocity, is blank the max velocity. It's twice, half, 1/3, 1/4, 1/5. What is it of the max velocity? So U mean is equal to something times U max. The mean, so if I have that quadratic or parabolic velocity profile, the max is right there, and half of the max is the mean. It's as if everywhere throughout had that mean velocity, so that the mass flow rate is equal to rho U mean cross-sectional area. And you find, oh, it's half. The U mean is 1/2 of U max. How did we get that? Well, you got that from your memory. Now let's see if it's on the next slide. Sure. So this is our equation for U mean, and we just solved for U as a function of R for a laminar fully developed flow. So we can put that in right here. And we're going to integrate with respect to R. The pi's cancel. We introduce a dummy variable of integration. I was talking to somebody, maybe they're in this room right now during office hours today. Remember dummy variable of integration in your calculus class? It's named after Professor Dummy in honor of, no, it's just, do you remember that funny term? I remember it when I took calculus. What? A dummy variable? What? That's kind of degrading. You know, anyway. So we have this new variable. I just call it R hat. You could call it tau. You could call it U. You could call it whatever. But you don't want to. You have already a lot of association with some variables. But you turn that integral here, and then you just perform the integration, and you come up with the mean is equal to times U max times 1/4. Boom! It's 1/2 of the max. It falls right out of the max of the calculus. Now, we can go back and do a forced balance on a section of the fluid, a control volume, for a control volume around it of a section of the fluid. The fluid is entering this control volume and exiting the control volume, but the linear momentum flow rate of the fluid is not changing. Because of that, for the entire control volume, the sum of the forces acting on the surfaces of that control volume, as well as any boundary, but I mean internal forces. The internal force is neglected because I'm not going to put it where gravity is pulling it one way or the other. Put it horizontal pipe. There needs to be a net force balance on it. So we have the pressure acting along the two end faces, and we have the wall shear stress acting along the circumference, along the length. And when you do that, what you get is that the wall shear stress has to match with the pressure gradient. So isn't this dP dx the pressure gradient? Let me do this. If my pipe is like this, right, and I have X running in the positive direction, start at 0 at one end, go off to maybe L. And I have the flow going that direction, in the positive X direction in the pipe. And it's a viscous fluid. Do I expect that the pressure will be constant? Answer A. Or the pressure profile would look like this, go down with increasing X, answer B. Or go up, answer C. What does the pressure as a function of X look like in my pipe? Are we ready? I think we're ready. Why are we not 100% correct on a question like this? I don't know. I mean, this is kind of, you can even leave math to the side, isn't it? It's just like, look it, if I'm going to push fluid down the pipe, I better have high pressure on one and low on the other. True? True? So the right answer is, thank you for the majority, 64%. It goes down. So that's why we tuck that minus sign in front of this term. Because if dP dx is negative, I put a negative in front of a negative quantity. Guess what is in parentheses? Positive quantity. So negative dP dx is a positive quantity. So, all right, let's press forward. All right, we had the Moody or the Darcy-Weisbach friction factor. Sometimes in this book, there's no subscript on it. It's just F. Sometimes in other books, they'll put a D, W, or a subscript D on it. And maybe you have to look again, what did they use in your fluids book? What name did they call the friction factor? So it's defined in this book, just F, without the subscript DW, but the Darcy or the Moody friction factor is called minus dP dx. Again, this term right here is positive. Minus dP dx is positive. All right. Times the diameter divided by 1/2 rho u mean square. All right, here's a chance somebody's really shy. I've emphasized this before. What is the term called that's 1/2 rho u mean squared? What's that called? Dynamic pressure. Absolutely. Very good. Thank you. Now, sometimes they'll write it like this. What happened to the minus sign? It's gone. Where's the dP dx? Gone. But if you go back and you think, here's that pressure as a function going from 0 to L. That's dx. So here you go from here to here. The pressure change that we're talking about, they're going to talk about a positive pressure drop. And so minus dP dx is a positive pressure drop divided by the length of the pipe. And so they'll replace it. And so sometimes it's written like this, and you say, there's a minus sign missing. No, there's not. They're talking about a positive pressure drop or a positive pressure loss. All right. How is this equation used? Well, this is actually the way I remember it. The pressure loss is equal to the friction factor, length over diameter times the velocity pressure or dynamic pressure. Let's keep going. So you go back to the laminar flow pipe, fully developed. And you can get a very simple relationship now that we have introduced that Reynolds number, we know it is, and we know the friction factor. We can get that the friction factor is 64 over Reynolds number. Look familiar? 64 over, only for fully developed laminar flow in a round pipe. Let's go on. How do we get that equation? Well, there's a couple places you can start. Maybe the easiest is just go back at this blue. What is that blue? We worked out what that mean velocity was for flow in a pipe. And then you say, well, I don't want it in terms of radius. Let's put it in terms of diameter. So you pick up 32 instead of 1 over 8, 1 over 32. And then you say, I'm going to multiply by unity. I'm going to multiply the definition of the friction factor by unity from this above equation. cancel terms, and voila, and recognize that it doesn't look that familiar right here, but this is 1 over the Reynolds number for flow in a pipe. Hence, the friction factor is 64 over Reynolds number. Can I use that, Professor, for maybe a Reynolds number of 20,000? Nope, only below 2,300, and only after it's been fully developed. Now, I am so glad that nobody that I know of uses a Reynolds number for internal flow in a pipe where the characteristic length is the radius. Oh, there's probably somebody out there in the world. I haven't seen them yet. But there's a lot of people in the world have a different version of the friction factor. It's named after Professor Fanning, who did a lot of work. All right, so this is in a lot of fluids dynamics textbooks, is they'll have a friction factor. Maybe they'll put a different subscript on it, or maybe they'll put C sub F because it's more closely related to the skin friction coefficient like we had for external flow. But anyway, it's tau W divided by 1/2 rho U mean squared. This is the shear stress at the wall. We had worked that out for laminar flow. There it is. So when you do a little plug and chug, you find out that either the fanning friction factor or the skin friction coefficient for internal flow, either way, is 1/4 the Darcy or the Moody friction factor. So, I hate to say it, sometimes they're a factor of 4. Sometimes somebody will say, oh, the friction factor for flow inside a pipe, laminar flow, completely fully developed is 16 over the Reynolds number. You say, that's a typo. They have a different definition of the friction factor. It's 4 times 16 is 64. So do you remember something like that in your fluids book? I hate to say it, but the world isn't consistent when it comes to friction factors. All right, now a review of pumping systems. Because it's not uncommon to have a closed loop piping system. And if you want flow to go all the way around in that closed loop piping system, it's not going to go all day and all night for free. You're going to have to stick in a pump or multiple pumps. The simplest is one pump. Now you think about the pressure at 2 versus the pressure at 1. And this is where it can get confusing. So you can think about the pump gain of the pump. That's going from 1 to 2. Wouldn't the pressure at 2 be positive compared to the pressure at 1? The outlet of the pump pressure is high. So you could talk about the pump gain. You can also think about the loss in the system. That would be thinking about, from 2 down to 1. So the piping loss, P loss, is P2 minus P1. Guess what? They're matched. What the pump puts up, the frictional losses in the piping brings down. So the piping gain, the pressure gain in the pump is equal to the pressure loss in the piping system. Very basic, true? Very good. Now, how do I get that boost in the pressure? Well, I have a pump. What feeds the pump? A shaft. What's feeding the shaft? The electric motor. What's feeding the electric motor? Wires, electricity. So we go back and we reviewed a little bit. Here's electricity. Not 100% of it's converted electric power into shaft power. Some is Q dot loss. And then the pump. Not all of the energy, mechanical shaft power coming into it goes into the fluid. Some is lost. True? All right. But we should be able to review that for electric motor, I have this power coming into it, W dot electric. Maybe it's in kilowatts. It's the product of, and I've given you half of the equation, the voltage difference between the two lines, and the what? Who wants to volunteer? The current. Now, if it's 3-phase, there's a factor. Does anybody remember? Square root of 3 it is. And if you have to work with 3-phase power, you'll have to deal with that one. And this is the RMS current and the RMS voltage. And there's also a PF, a power factor. So life isn't as easy as this, but this is the basic idea. It only gets worse. All right. Now, how about a shaft? This is where the mechanicals take charge, right? I have a rotating shaft. It's transmitting some torque in it. What is the shaft power? The torque, I've given you half the equation. What's the other half? Omega. What is omega? Rotational speed. It's this rotational speed, true? So this is our rotational speed. All right, now this is where I really wanted to get to. We have something, this power flows into the fluid. We said the purpose of the pump is not to flow power into the fluid, just to increase the pressure. No. You can look at it from an energy and a flow of energy perspective. That was emphasized in our fluids class. So the fluid power is the product of half of the equation I've given you, the pressure gain times, don't call it out. Don't call it out. You got it? You know it? Did you take fluids with me? Twice, yeah. I'm not teaching heat transfer next semester, so we can't look forward to a repeat. You got to get through it this semester. All right. Chris, go ahead. Yeah, it's a flow rate. Flow rate. So let's take a look. Next page, I have a question for you. So the fluid power is a product of the pressure gain across the pipe times what? And here are the clicker options. We just said it was a flow rate. And I'm going to start with a big hint over here. You can use units to really clarify this. And the way I like to look at pressure, everybody knows pressure is force per unit area. Newton's force per unit meter squared area. But if I multiply the numerator and the denominator by length over length, what happens to the area times length? That's a volume, L cubed. Area times length is a volume. And what's the force times the length? Work. Integral F dx. Go way back to mechanics. It's a work term. All right. So you can work this out by units, but I'm going to open it up now for a clicker response. I'll give you plenty of time. Work it out. What do I need to multiply by to get this equation to be correct? All right, let's stop this. All right, so let's continue on with this hint. So if pressure is energy per unit volume, and I want to multiply this by something, I'm going to multiply pressure by something such that I get W dot. What is W dot? That's power. That's energy per unit time. So I have energy per unit volume. I want to multiply by something to get energy per unit time. True? Can you see what I need to multiply by? How about volume per unit time? So now I'm really clear on the flow rate. Is it a mass flow rate? No, that would have been mass per unit time. It's a volume flow rate, isn't it? So now I just look for which of these terms is a volume flow rate. And somebody want to call it out? C. Very good for C. All right, so that's the answer. Let's move to the Moody diagram. It's a good compilation of a lot of data. So what's on the x-axis? What's on the x-axis? The Reynolds number. And when you have low Reynolds number, what type of flow do you have? Laminar flow. So this is 1,000, that's around 2,000. Below, that's the laminar region. So the vast majority of the x-axis is out in the turbulent region, is it not? And then you go 10 to the 4, 10 to the 5. Hey, is that a log plot or a linear plot? It's log. And you can cover a large range of numbers. These are huge Reynolds numbers. They are very, very fast flows, often not encountered in engineering. A lot of engineering is in this range of Reynolds number. A lot of engineering. Okay? Now, what's on the y-axis? Our friction factor. Ooh, this one's a harder one. Is that a log scale or a linear scale on the y-axis? It'd be a lot easier if there were a bunch of like 10 to the 4, 10 to the 5, 10 to the 6. But there isn't, is there? So, like this is called 1 order magnitude, 1 order magnitude, 1 order magnitude. If I go from 0.01 up to 0.1, that's 1 order of a factor of 10. Okay. Now, if this would have been 0 and that would have been 0.1, what would have been right in the middle? Half of that, right, 0.05. Is 0.05 close to it or a little smidgen up higher? The numbers close to the next decade are crammed. This is a log scale. You look at it for a while and you figure out, oh no, that's not linear, it's log. All right? All right, so why did they put it on a log-log scale? They probably could have put it on a linear log scale. Why? Because this line is either a straight line or a curved line on a log-log plot. The laminar flow, F is 64 over Reynolds number. We developed that for the friction factor. Guess what? You put on a log-log plot, it's a straight line. You put on a linear log plot, it is not a straight line. Everybody plots a Moody diagram on a log-log plot. And it's a nice, easy to see, boom, straight line right there. What's the slope? -1. Yes, sir. Yes, these are all fully developed flow conditions. That's right. In most engineering applications, well, on the entrance region, you have a little more friction dissipation or pressure drop. So usually you just adjust a little bit for it. All right. Now, out here, you have turbulent flow. True? What does each of these red curves, let's say this one, what does that represent? A line of constant what? Line of constant relative roughness. That's a line of constant relative roughness. So the relative roughness is not plotted on this y-axis on the right-hand side. No. Those are just showing you different values of relative roughness. So this curve of 0.02 is the line of constant relative roughness. So the friction factor is, in general, a function of the Reynolds number and the relative roughness. True? All right. Professor, what's this dashed line for? It separates two regions of this turbulent region. All right? So everything is unique that's over on this side of it to the right versus everything that's below it to the left. All right. Well, they give this region out here a name. It's the fully turbulent, fully rough zone, etc. There's a couple ways of saying it. This book has fully rough. How about this region in here? It's called the transition zone. Why doesn't it continue to go over here? Well, the edge of it is for what type of pipes? Or smooth. That's where you have really smooth pipes. So in this region, it's a transitional zone. It's turbulent. And they go from these curves. This is a smooth pipe curve. And then they peel off at different relative roughness. What's key out in this region? Let me see if I have a question on the next page. Aha. In the fully rough zone. Where's the fully rough zone? Out here. For a given relative roughness, the friction factor is answer A, B, or C. And that's exactly right. Out in this region, for a given relative roughness, the friction factor is no longer a function of the Reynolds number. So if I'm given, let's say this is the relative roughness and I'm out in that region, if I double the Reynolds number, speed it up, or I slow it down, cut it in half, did the friction factor change? No, that's the key idea. That's why they separate. But in this region, sorry, you're going to have to, if you want the friction factor, you're going to have to give the Reynolds number as well as the relative roughness. Well, what happens if it's very, very smooth? Well, if it's very, very smooth, that's essentially 0, and then this is that bottommost curve in that zone. Do we have a lot of engineering applications with very, very smooth pipes where the relative roughness is small? I can just assume it's a smooth pipe. Yes or no? Yeah, a lot. All the PVCs are very, very smooth unless they get corroded and junk. And if you ever taken anything apart after a few years in service, there's a bunch of corroded junk in there too. But anyway, drawn copper tubing, very smooth when it's brand new. So a lot of applications have very low relative roughness. Well, you can even come in and find a friction factor curve fitted, and it'll look like something like this. This is the Blasius correlation. I can't remember if the Blasius correlation's in this book or I got it out of another fluids book or heat transfer book. You'll see that, and at first you're like, what? And then they say this correlation's good for Reynolds number less than 10 to the 5. Here's 10 to the 5. So don't go out larger. And for smooth, basically they curve fit this bottom for the smooth. Why? A lot of engineering applications are at modest turbulent flow numbers and in smooth pipes. And so you can curve fit and fit it like that. Well, I didn't cover everything that you learned in fluid mechanics relevant for internal flow, but I covered a lot. And next time I have to move into thermal considerations. But believe me, if your foundation's strong in fluid mechanics, the rest is pretty easy. So with that, we're going to pass out the quiz. And thank you for your attention.